Today we're going to look at an example of a nice style of puzzle which is pretty common in math contests or maybe in problem-solving books. And that's the type of puzzle that starts with a bunch of numbers written on a chalkboard and then answer something about what is done after that process. Okay, so anyway, let's look at the particular problem that we're looking at today. So the numbers 1, 2, 3, up to 2023, that's the current year, are written on a chalkboard. We randomly choose two numbers, erase them, and write the sum of them and their product. And then we repeat. And then our question is, what are the possible values of the last number? So we're going to start with some exploration, and that exploration will be on smaller cases. So in other words, instead of having 1, 2, 3 up to 2023, maybe we'll just start with 1, 2, 3. Okay, so let's do that. So let's start with 1, 2, 3. And notice we have to randomly choose two of them. Let's see, where's that? Randomly choose two of them, erase them, write the sum of them and their product. So of course there's a couple of ways to randomly choose the first two. There are in fact three ways. So I'm actually going to write 3 copies of this just to see what all of the possible outcomes are. And maybe for this first copy, I'll choose 1 and 2 to be my first randomly chosen numbers. For this second copy, I'll choose 2 and 3 to be my first 2 randomly chosen numbers. And finally, for this third copy, I'll choose 1 and 3. Okay, so choosing 1 and 2 means we need to erase 1 and 2, and then we'll include 1 plus 2 plus 1 times 2. So that's the sum of the original numbers and their product. But now let's rewrite this list a little bit. So this list can be rewritten as, let's see, 2 plus 2 plus 1, so that's 5 and 3. But now from there's only one thing you can do, because if we randomly choose 2 elements from a set of 2, well, there's only one way to do that. So let's see, that's going to take us to, well, it's going to be 3 plus 5 plus 3 times 5. And you can calculate that, and that will be the number 23. Okay, so, well, at least in this case, 23 is a possible outcome. Well, let's see what we get if we start with 2 and 3 being grouped. Okay, so that means after my first step, I'll have 1, and then I'll have the number 2 plus 3 plus 2 times 3. Again, the sum of the original numbers and their product. But now let's rewrite that, doing some arithmetic here, and that will be 1 and, let's see, it'll be 2 plus 3, which is 5, plus 6, so that will be 11. And now we need to do the same thing again. So if we do this one more time, we'll get 1 plus 11 plus 1 times 11. If you multiply and add all of that up, you'll get 23 again. So this is seeming pretty suspicious already, because there's no reason we should expect to get the same number twice, unless of course it's likely to always get the same number. But actually, maybe this is a special case of choosing consecutive numbers first. So let's check this last case where we choose as our first pair 1 and 3. So that means we're going to replace this with 2 and then 1 plus 3 plus 1 times 3. And then after some simplification, that'll be 2 and 7. But now let's apply the procedure again. And that'll leave us with 2 plus 7 plus 2 times 7. So that's going to be 9 plus 14, which, again, that is 23. So now we have a little bit stronger evidence. All of the possible ways of churning through the numbers 1, 2, and 3 net us out with the number 23. So let's maybe do another little experiment on the number 1, 2, 3, and 4. We won't go through all of the possible cases, but we'll go through a couple of them. Okay, so 1, 2, 3, 4, like I said, and 1, 2, 3, 4. So we'll go through 2 cases. And we'll do these in 2 pairs, which of course is not necessarily the way you have to do it, but it is a way you can do it. So let's start by pairing 1 and 2 and 3 and 4. So let's see. that's going to lead us to have what? Well, we'll have 1 plus 2 plus 1 times 2. Well, we've done that before and we had the number 5. And then we'll have 3 plus 4, which is 7, and then plus 3 times 4, so that's 7 plus 12, so that's 19. So there we have 5 and 19. Okay, so now let's apply the rule again, leaving us with 5 plus 19 plus 5 times 19. Notice that we can take this 5 and this 5 times 19 and turn it into 5 times 20. Thinking about like 5 as maybe being like a variable for just a second. But 5 times 20 is equal to 100 plus 19 is 119. And now let's do this by doing a little bit different pairing. So let's pair 1 and 3, and then 2 and 4. And let's see what we get out of that. So let's see, 1 paired with 3. Well, we've already done that, and we got 7. So that's going to be 7. And then 2 paired with 4. Let's see, that's going to be 2 plus 4, which is 6, plus 2 times 4. 2 times 4 is 8. So 8 plus 6 is 14. So we'll have 7 and 14. So now let's apply the rule again, and we'll have 7 plus 14 plus 7 times 14. But if you multiply and add all of that out, you'll get 119 one more time. But notice we get 119 for both of them, so it seems like we are always going to get the same number. Now we just have to figure out some sort of pattern for this number. Well, let's see, 23, 119. Well, what I notice about those is they're one less than a factorial. 4 factorial is 24, 5 factorial is 120. Oh, but this ends at 4, so maybe we could really think about this as 4 plus 1 factorial minus 1. So we boost this 4 up to 5, we take its factorial and then subtract 1. And then likewise here, we have 3 plus 1 factorial minus 1. So just to be clear, here we're ending at 3, and we go up to 3 plus 1 factorial. Here we are ending at 4, and we go up to 4 plus 1 factorial. Okay, so let's write down what we think is a conjecture and then talk about how to prove that. Okay, so on the last board we formed the following guess, and that is if we do this procedure for the numbers 1, 2, 3 up to n, we should end with the number n plus 1 factorial minus 1 on the chalkboard. But that really doesn't answer this question, and that is how do we account for the random choice? And our strategy for accounting for this random choice is taken from a solution that I found on the Math Stack Exchange. That's the number over there. And so let's let A1, A2 up to AN be a reordering of 1, 2, 3 up to n corresponding to our random choice. By that, I mean A1 and A2 will be the first 2 numbers that we combine together using this procedure, and then so on and so forth. Okay, so let's kind of explore what's going on here so we can get an idea for how our argument will go. So let's start with A1, A2, A3. And since this ordering corresponds to our random choice, we'll go from this direction to this direction. So that means we'll start with A1 and A2. That means we need to replace this with A1 plus A2 plus A1, A2. And then we have A3 there. Now we're going to do that one more time, and that'll leave us what? So it'll be something like this. We'll have A1, A2, A3 plus A1, A3 plus A1, A2 plus A2, A3 plus A1 plus A2 plus A3. So I've obviously reordered some things there. So the important thing to notice is we have a cubic term in A1, A2, A3, all of the possible quadratic terms where none of the terms are repeated, and all of the possible linear terms. So this is very, very close to being the product of A1 plus 1 with a2 plus 1 with a3 plus 1. The only way this differs from this product is that it does not include the number 1, so we can subtract 1 and then we have an equality. Okay, but now let's notice that this is equal to the number 2 times 3 times 4 minus 1, in other words, 23. And that's because we know that A1, A2, and A3 come from the set 1, 2, 3. And none of them are equal to each other, so they're all distinct elements of this set. But notice this product is going to simplify to 2 times 3 times 4, regardless of which order it's in. So I think that's kind of the idea of how this is going. Now, I think we can maybe add something to our statement up here, and that would be the final number is, so let's see, I think it should be something like this. A1 plus 1 multiplied all the way up to an plus 1 minus 1. So that should be the final number. And that's kind of based off of what we have right here. And of course, if a1 up to an is a reordering of 1, 2 up to n, then this is most definitely going to exactly be n plus 1 factorial minus 1. You know, because of this kind of thing happening right here. Okay, so now let's prove that blue box result using induction. Now we'll prove this blue box result, which will finish everything off. And we'll do this by induction. Notice our base case is essentially done. Well, we did the n equals 3 case, but you could also do the n equals 2 or 1 case as a base case if you want. So technically for doing the n equals 3 case, we're only proving this for values of n bigger than or equal to 3, but I think that's okay. All right, so what we'll start with is an induction hypothesis. So suppose for some k bigger than or equal to 1, we end with the number a1 plus 1 multiplied all the way up to ak plus 1 minus 1. And now let's also say we start on the board with a1, a2, a3, all the way up to ak, and then ak plus 1. And these are put in the order of combination. So what we'll do is we'll take these first k elements, and since we're combining from the left to the right, because again, we chose our ordering to correspond to our random choice, we know exactly where these should end up. And they should end up with that number right there by our induction hypothesis. So I'll write that down. So a1 plus 1 multiplied all the way up to ak plus 1 minus the number 1, and then comma ak plus 1. Great. So that's where we end after, you know, a bunch of steps. But I'm going to introduce a little bit of notation to keep this simple. I'm going to rewrite this as the number capital A. And now let's apply our procedure one last time to combine those two numbers. So recall, we're going to have their product. So that will be A times AK plus 1 minus AK plus 1. And then plus their sum. So that'll be plus, let's see, A minus 1 plus AK plus 1. But let's notice that this and this cancel. And then we can factor an A out of this term and this term, leaving us with, let's see, A times A sub k plus 1 minus 1. But now let's replace that capital A with what we renamed it up here. And now we have the product A1 plus 1 all the way up to AK plus 1 minus 1. But that's exactly what we needed to do to prove this by induction. But that means we've proved this blue box up here. But then if A1, A2, all the way up to AN are really just a permutation of 1, 2, up to n, you know, like we've said, then this product right here is exactly the same as the product 2 times 3 up to n plus 1, and then we have this minus 1. But that product 2 times 3 up to n plus 1 is exactly n plus 1 factorial, so that gives us our result. So we proved a more general case for sure, but definitely that answers our problem. So with our problem, the number is 2023. So that means our final answer for this setup will be 2024 factorial minus 1. So that's a fairly large number, but that's what we get. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.